So we will make a start. So thank you for coming, small number of people which could come. Those of you which couldn't come, hi, people on video. No, I'm catching on video. Hi, people who are watching video. So, unfortunately, the snow yesterday meant that classes were cancelled. Expeditions and all that kind of thing. But the way this course is designed, we try and do everything in order, and since we've got a practical class on Thursday, we kind of need to try and get through our stuff before then. Gosh, this place absolutely sucks. Never mind. I'll use my phone since our university is completely unable to actually do things themselves. So today what we're going to talk about is the first of our statistical tests, which is called the t-test. Now, just before we get that far, I want to talk a little bit at the start about hypothesis testing. This is a major thing for us to understand, is about testing hypotheses. So, just once my slides update, processing 1,000 files. It's not really. Then we can start. Thinking 120. It's 59%, 100%, there we go. Great. Okay. So, everyone got a hand up? Okay. Okay. So, there's basically two big questions in experimental sciences. Okay. Question number one: are these two things different from each other? And question number two: are these two things related to each other? And what we want to do in the first, couple of weeks of this course is look for differences. We want to say is, we've got these two samples, sample A and sample B. Are they different from each other? Right? This is an important thing for us to understand. So I want you to think about hypotheses first. So we all hopefully know what a hypothesis is, okay? It's a statement that we make about the world that we believe to be true. We have a guess about how something works. We say, I think that this system works by these rules. And then we say to ourselves, well, if that's true, I can make this prediction and then I can test that. So a hypothesis is basically, it's a statement about the world that we believe to be true and that we're going to test. Okay? Now, if a hypothesis is correct, then whatever experiment you do, it's going to be able to predict it, right? So, if we have a hypothesis, okay, that there's this stuff called gravity, okay? If I let go of this, what do you think is going to happen? It's going to fall, right? So, and it falls, okay, good. Excellent, I don't want to break it. Actually, I'll get something that I don't mind. Okay, my lecture notes, because they're terrible. So if I get this right, and I make my hypothesis, okay, there's this stuff called gravity, and that objects emit gravitational fields, and that they are going to attract each other, right? Okay, the Earth is going to attract this, right? And that this is going to attract the Earth, okay? And if I let go of it, my prediction is going to be, my hypothesis is, if I let go of this, it will fall, okay? And I let go of it, and it falls, and it doesn't break, which is good. And then, okay, so I tested that time, and I run the experiment again. Okay, I run it again. Okay, I run it again. This is just a really good excuse for littering, basically. Okay, so if we run that a million times, we would expect that in a million cases it would fall to the ground, right? Okay. But my hypothesis might be wrong. Maybe gravity isn't really true, right? Maybe it's not really true. But if the hypothesis is false, it could still explain the observations in some cases, right? It could be wrong, because, you know, like, we know that gravity is not really completely true, right? Because we know that Einstein's theories have superseded Newton's ideas, right? So we know that gravity itself it's not completely right. We don't fully understand it, okay? And you can go even further, because we know we've got quantum theory, right, which is the really small, and then you've got relativity, which is the really big, and they don't play well together, right? They don't work together, okay? Each one works really spectacularly well individually, but you can't make them fit together. So quantum theory and relativity at some level must be wrong. In which case, our ideas of gravity at some level must be wrong, right? But if I drop this, it's still going to fall to the ground, right? So even if our hypothesis is wrong, it could still explain an observation, right? But it could be wrong, okay? But if our hypothesis is wrong, there's some experiment out there somewhere that we could do that would prove it wrong, right? There is some way to test it and prove it wrong if it's actually wrong, okay? Okay. So the logical thing here, okay? We can't we cannot demonstrate hypotheses to be true because of condition 1 here, right? You can't tell the difference between this one, it explains observations made in experiments, and it explains observations made in experiments. Because of this and this, you can never say that a hypothesis is true. But you can demonstrate a hypothesis to be false, right? That's super easy, actually, okay? Now I'm going to give you a little example of this, okay? So let's imagine that we make a hypothesis that all swans are white, okay? Seems like a reasonable hypothesis, okay? So what we're going to do is we're going to test this by going out and looking at swans. Here are some swans. All white, yes. So that's a little bit of evidence for our hypothesis, yeah? Okay. Here are some more swans. They're also white. Well, our hypothesis is looking really good now, right? Must be true, right? Must be. Okay, so we'll look at some more swans, and yes, more white swans, okay? So this is looking good for our hypothesis so far. Here are some more swans, and also white, okay, great, okay? Let's ramp this up a little bit, okay? Here's lots of swans, okay? Lots and lots and lots, and they're all white, okay? So our hypothesis, all swans are white. It looks unassailable at this point, right? All swans are white. It's obviously true. All of our evidence shows that this is true. And then we look on the internet and we find this photograph. Okay. Okay. Anyone ever been to Australia, New Zealand? No? Okay, I lived in New Zealand for 2.5 years after I finished my PhD. In the Southern Hemisphere, swans are black. So, you can see from this, right? Let's go back to that first slide, okay? So, my hypothesis, right? If it's correct, if my hypothesis, all swans are white, is correct, then we can look at millions and millions and millions and millions of swans, and they'll always be white, okay? If my hypothesis is false, now we know my hypothesis is false, right? Because we just saw a black swan, right? Okay. But we looked at lots of swans, and they were all white. right? We looked at lots of pictures, lots of swans, and they were all white, right? So we know our hypothesis was actually false. But if we looked up, if we just didn't see the last picture, we couldn't tell the difference between these two, right? But it just took one black swan to do this. Just one. So logically we can never prove hypotheses to be false, to be true, right? But we can prove them to be false. Okay? So this is the kind of the basis for experimental hypothesis testing in science. Swans, lots of swans, look, hypothesis is doing great. And then boom, okay, our hypothesis is false. All swans are not white. Or not all swans are white. Okay? Okay, easy peasy. So what we're going to do in science is that we're going to test if our hypothesis is false rather than if it's true, right? Because we can never get to truth. We can never get there. Right? We can never collect enough data. But we can show if it's false. Now, we consider hypotheses to be true if we test them and we cannot falsify them, right? So let's imagine that we go out and we say, all swans are white, and we go out and we look at our local pond and we see all the swans there are white. So we go to the next town over and we look at all the swans there and they're all white. We go to the next town over and we look at all the swans there and they're all white. Wherever we go, we always find white swans and we never find any other colour, right? We could accept that our hypothesis is probably true. We could never say 100%, right? But we could get to 99% certain or something like that. Okay? So, if we try and disprove our idea, but we can't disprove it, it might be true. It definitely is true, but it might be true. So, you can never get to 100% certainty for positive claims, okay? Now, normally when we're doing an experiment, we're testing a sample of the population. We're not looking at the whole population, right? When we looked at a picture of swans there, we weren't looking at a picture of every swan in the world, right? Only a few. So, if we only looked at swans from around here, we might just accept that all swans are white hypothesis. But if we take a trip to Australia, we're going to reject our all swans are white hypothesis. Okay? So, you have to represent all the data fairly. Okay, that kind of goes without saying, I think. And what we want to do is we want to try and quantify, we use statistics to quantify the probability that our hypothesis is wrong. This all sounds very abstract at the moment, okay? But I do want you to think about it because it's really important, number one. And number two, there's a homework question on it, okay? So, I really want you to understand this idea, okay? That it's really hard to prove things are true, but it's really easy to prove something's false, right? You just need one piece of data can prove your hypothesis, okay? If I have a hypothesis that my wife is being completely honest and faithful to me, right? And I might be very happy and convinced in that because I see all her behaviours and all those sorts of things. But if I get a photograph of her, with another guy in a compromising position, that would disprove my hypothesis straight away, right? So, if you think about it this way, that, I can never prove 100% something to be true, but it's really easy to prove it false. That's the idea behind experimental testing. Okay, so often in science we want to look at two groups, a control group and a treatment group. And we want to know whether or not these two groups differ significantly from each other. So an example here might be that we have a new medicine. Okay, so we've got the old medicine and we've got the new medicine. And is the new medicine better than the old medicine at reducing blood pressure? Okay, or curing cancer, or whatever it is. Okay, so we've got our control group and we've got our treatment group. Our control is the old medicine, our treatment is the new medicine. Does a new fertilizer increase plant growth rates? Okay, is it better than the old fertilizer, or is it better than no fertilizer? Okay, and again we can have our control, we can have our treatment. And what we want to do is we want to understand is, are the means significantly different from each other, or are they, or do any differences result from random chance? Okay, so I'll draw a little diagram on the board because I love diagrams. Okay, so let's imagine that we've got our two things here. We've got our control, which we're going to label 0, and our treatment, which we're going to label 1. Okay, and we've got, let's say, grass growth. Okay. Okay, and for our treatment, okay, for our control, our data is like this, okay, that we've got a cloud of data, and they all grow about this much. And we can do a mean, and we can do a standard deviation, and we can do standard errors, and all those kinds of good things, right? And then we've got our treatment, okay. Now, I'm going to actually do I'm going to do 1A, I'm going to do 1B. Okay, so let's imagine we've got 1A here, okay? Okay, so maybe the mean is a little bit higher, but there's quite a bit of variability in the data. Now we know that if we took a different 50 samples, then we get a different mean value. Maybe not very different, but a little bit different, right? And we can quantify, how certain we are about this mean by looking at the standard error. Okay, we talked about that last week. But what if we've got 1B, right? 1B, all our data is up here, okay? And we calculate out our mean. And we can calculate out standard deviations and standard errors and all those kinds of good things. We might look at this and say, they're different from each other, right? We might look at these two and say, are they different from each other? Well, probably not, right? They're probably not different from each other. Probably just random variability. But this one is probably different from this one over here. Yeah? And that's what we want to test in this week, right? This is what we're looking at as t-tests. So, we're going to start with a fairly simple measure here. A thing called a one-sample t-test. Now, a one-sample t-test, basically what it's going to tell you is, we have a sample, and then we have a fixed point. And we want to test, is the sample mean different from that fixed point? Okay? So, I'm going to give you an example, and hopefully it's going to become clear. So, let's imagine that we've got this vitamin Y, okay? And it's an essential vitamin, right? It's really important. But too much of it's harmful, right? So your body needs it, but if you have too much, you'll die, okay, you get sick. So the FDA, okay, or the Japanese equivalent of the FDA, sets standards for vitamin Y content and of vitamin pills, okay? And the vitamin pills have to contain, on average, 100 units, okay? So what we say is the pills have to have an average of 100 units. Now we know that there's going to be some variability, right? Some pills, even if we say we want the pills to be at 100, and then we make thousands and thousands of the pills, some of them will be a little bit above 100 and some will be a little bit below, right? Okay. But on average it should be 100. So a manufacturer, vitamin Y pill manufacturer, okay, decides that they're going to get one of their biochemists, okay, and the biochemist goes out and measures 100 pills. And she finds that the sample mean is 100.5 units, okay, and it has a standard deviation of 2.19. Okay, easy. Everyone happy so far, right? So we know what means, we know what standard deviations, okay. So we're looking for 100. We've actually measured 100.5, and we've got this standard deviation of 2.19. Okay. So let's look at our hypotheses. So we've got our null hypothesis. Okay. Our null hypothesis is going to be that our mean vitamin Y content is 100. Okay. That there's no difference between our set point, 100, and the real mean. Okay. So no significant difference in vitamin Y concentration in 100, okay? And our alternate hypothesis is that our vitamin Y content is not 100, okay? So this is a true dichotomy, right? This is a logically true dichotomy. It's either A or not A, right? It's not A or B, it's A or not A, okay? Let's think about this from a sort of legal standpoint, right? Because the law actually is pretty sensible on this one. What's the opposite of guilty?
Not guilty.
Okay, I've got two answers here. I've got innocent and not guilty. Who thinks it's innocent? Who thinks it's not guilty? Good. Okay, most of you think it's not guilty. That's true. Okay? Guilty and innocent are not the same. Are not opposites. Okay? There's guilty and not guilty, and there's innocent and not innocent. If you go to a court of law, then what they do is they test whether or not you're guilty. They don't test your innocence. That's a different question. They test whether or not there's enough evidence to conclude that you are guilty. So there's guilty, not guilty, innocent and not innocent, right? So there are actually two different prongs, guilty and innocent, okay? But we can only test one at a time. So we test guilty and not guilty. In this case, not guilty and guilty, okay? So what we want to do is we want to evaluate whether or not the null hypothesis is likely to be false. Now, the logic on this is a little bit difficult, right? But I've got a very helpful flowchart which can help you out a lot. Okay. So, I need to rearrange my screen here because my screen size is not actually the same. Okay, null hypothesis, V, null hypothesis, mean vitamin Y content is 100. Okay, alternate hypothesis, mean vitamin Y content is not 100. Okay. So let's start off with a question. Is the measured value 100? Okay, so there's two possibilities. It's either yes or no, right? If the measured value is actually 100, then there's two possibilities. Number one, the null hypothesis is true. So if our null hypothesis is it's 100 and we measure 100, possibly the null hypothesis is true. Okay? But there's another possibility. The null hypothesis might be false. And it could just be that we just happen to choose 100 pills that just happen to give us a value of 100. Could just be a random chance. But we don't have any evidence for this. We don't have any evidence that there's a coincidence here, right? So we just accept our null hypothesis. So if our null hypothesis is the vitamin Y content is 100 and we measure 100, just accept the null hypothesis, right? It's probably true. It might not be true. You know, logically it might not be true, but you don't have any evidence for that, so give up. Okay, the other possibility, our measured value is not 100. Okay, now again there's two possibilities. Possibility number one is that our null hypothesis is false. And if our null hypothesis is false, that would mean that our alternate hypothesis must be true. Right? If this is not true, this must be true. Right? Because that's a logical pair, right? Okay. But there's another possibility. It could be that our null hypothesis is actually true. This is sounding nightmarish, isn't it? Sounds terrible. How can we actually find these things out? So it could be that the real value really actually is 100, but we, for whatever reason, for a random chance, we got a result that was not 100. Okay? And we can use the one sample t-test to determine how likely this is to be. Okay? And if we say that this is probably not true, if we can say this is probably not true, then that would mean that this is true, or probably is true, right? Okay. So, let me just run through that again. Okay, one more. Is our measured value 100? If yes, maybe the null hypothesis is true, maybe the null hypothesis is false, but we don't have any evidence for saying that, so just accept the null hypothesis, right? If we did have some evidence that the null hypothesis is actually false, and that our sample was skewed for whatever reason, then maybe we could go and do another experiment. But within this experimental setup, we just have to accept the null hypothesis, right? Null hypothesis, determine y content equals 100, we measure 100, the null hypothesis is probably true. Okay. What if we don't measure 100? Okay? Then there's two possibilities. Either the null hypothesis is false, right? Because, is it 100? No. That's wrong then. Okay? So, maybe our null hypothesis is false, and therefore our alternate hypothesis is true. Yeah? Everyone happy? Okay. But there's another possibility that our null hypothesis is actually true, but we just happened to get 100 pills, which just happened to give us a value that was not 100, but actually the real mean actually is 100. Right? We just happened to get 100 pills that were just artificially high. Right? Just for whatever reason. Okay? It's unlikely, right? But it's possible. Could happen. Okay? So the real value is 100, but random chance gave us a value that was different. Okay? And what we can do is we can quantify how likely this is to be true. Okay? And that's what the one sample t-test, the one sample t-test is all about. It'll make a little bit more sense. Okay, so here's your graph. We've got our proportion of pills up here. We've got our vitamin Y content up here. This is the wrong size, this slide. Anyway, never mind. When I do my presentations, I break so many rules that I'm going to tell you not to break in technical English too. Don't worry about it. I'm a bad example. Okay, concentration vitamin Y along here. 90, 92, 94, 96, 98, 100, 102, 104, 68, 10 milligrams, yeah? Or units, sorry. Up here, the proportion of the pills, okay? So we can see our black line here, okay? This is our normal distribution. Our mean is 100.5, okay? One standard deviation, 2.9. Two standard deviations, 4.4-ish, okay, 4.38. What percentage of pills would we expect to fall within one standard deviation? 68%, right? What percentage of pills do we expect to fall within two standard deviations? 95.4, right? Okay, good, excellent, good. So we expect 95.4% of data points to lie in between these blue lines, yeah? Everyone happy with that? Okay, good, good. That's our standard deviations, but of course we can also calculate our standard errors. And standard errors tell us about what? What's the difference between standard deviation and errors? What do standard errors tell us? It tells you about how accurately you can estimate the mean, right? So if we took lots and lots of pills, we took, hundreds and hundreds of pills, and we measured means for each one of those groups, right? That would give us a bunch of means, and if we take the standard deviation, that gives us the standard error. Okay. So if we look at our standard errors, here's our probability of our mean. Okay. Now we measured 100.5, so our mean distribution has to be centered on that. And here's our red line. Now, here's our one standard error. Okay? So there's a 64% chance, or 68% chance, that our real mean for all of the pills in the world, there's a 68% chance it falls inside these lines. And there's a 95% chance it falls inside these lines. Okay? So this tells us, this is the mean that we actually measured. But if we measured a different 100 pills, we would have got a different value. It wouldn't have been 100.5. It might have been 100.4, it could have been 100.55, but it wouldn't be 100.5, right, if we measured a different 100 pills. Okay? It would be somewhere around here, but it wouldn't be exactly the same value. Okay? There's a 68% chance that if we measured another 100 pills, right? This we measure the vitamin Y content of another 100 pills. There's a 68% chance that the mean that we would measure for the second group would be inside here. And there's a 95% chance that that second mean would fall inside these blue lines. Does that make sense? Is anyone really scratching their head about that? And it's not simple to think about, and probability is not an easy thing to think in, right? But hopefully you can kind of get that idea. Go and watch the video again later, and you'll should get clearer, okay? So, as I say, if we went and measured another 100 pills, we would get another mean value that would be around about 100.5, probably. But it probably wouldn't be exactly 100.5, okay? It might be 100.4, or it might be 100.6, okay? But it would be around about here. And as I say, there's a 68% chance it would fall inside these lines, and there's a 95% chance it would fall inside these lines. Okay. So, there's a 95.4% chance that the real mean for all the pills in the world fall inside these lines. Okay? Now here's a little problem for you, right? This is the mean that it has to be 100.0. And 100.0 doesn't fit inside these blue lines. Right? This blue line comes here. And in fact that's a value of 100.062 is this point here. So what does this say? This says that there is, what, a 97%, I suppose. There's a 97% chance that the real mean is above 100.0. Right? Because it could be anywhere up there. There's only a tiny, tiny, tiny little chance that the real mean value is actually 100. Okay. Now, we don't have to plot out graphs to do this every single time. Okay? There's a better way of doing this. There's a mathematical way of doing this. Okay? Unsurprisingly. So what we want to do is, we want to test the difference between the estimated mean and the measured mean and the hypothesized mean. Okay? Well, I suppose it's the, we measured 100 pills. That's our sample mean. Okay? I'm going to write this up on the board. So we've got two means here, okay? We've got our sample mean. So 100.5, yeah? Okay. And then we've got our estimate of the population mean. Which is 100.5. You might say, well, they're the same number. Okay. Our sample mean, 100.5, that is the measure for these 100 pills. Okay. For those 100 pills, The mean is 100.5. Absolutely is. That 100.5 is also an estimate for the population mean, for all the pills in the world. Right? So it's the same number, because we use our sample mean as an estimate of the population mean. What we want to know is the population mean. We want to know what is the mean value. If we measured all of the pills in the world, what's the mean value that we actually get? Okay? Now we can't measure all of the pills in the world. Number one, it's too much work. Number two, our employer would go bankrupt because they would have nothing to sell. Okay? We can't measure all the pills in the world. But we can estimate what that value would be by taking a sample. Okay? So our sample mean, 100.5, that's that 100 pills. That's actually true. This is true. This is an estimate. Right? The population mean, we don't know. We don't know what the actual value is for all of the pills in the world. Okay? But we know it's probably around about 100.5. We know it's around about 100.5 because of the sample mean. Our population mean, there's a 68% chance that if we measured all of the pills in the world, there's a 68% chance that we'd be within one standard error of our sample mean, and there's a 95% chance that we'd be within 2 standard errors of our sample mean. Okay? The population mean, 68% chances in here, 95% chances in here. Okay? This in here doesn't include 100. What this means is that we would say, in science, we'd say that this 100.5, it's statistically different from 100. Right? So we want to do the math on this now. We don't want to, but we're gonna. Okay? Okay. So, estimated mean, our sample mean, which is the 100 pills. Okay? Boom, boom, boom. But this sample mean is also an estimate of the population mean. Okay? So our estimated mean, okay, which is 100 pills measured, X bar. Okay? Hypothesized mean, mu. Okay? 100. 100.5 minus 100 gives us a value of 0.5. I like your math skills. Okay. And our standard deviation. Well, we know our standard deviation is 2.19, right? And we know our number of samples is 100, right? We measure 100 pills. So square root of n. So basically this is the standard error. Right? Down here, this is the standard error. So this is the difference and this is the standard error. Okay. So X bar is our sample mean, 100.5. Mu is the hypothesized mean, 100. SD is the standard deviation, 2.19. N is the number of pills in the sample, 100. So the lower line is the standard error. And T essentially is how many standard errors is there between our estimated mean and our hypothesized mean. So when we do that mathematically, it'll make more sense, right? 100.5 minus 100 is 0.5, yeah? Okay. So 0.5 goes up here. Okay? 2.19 divided by the square root of 100. The square root of 100 is 10, right? Okay. So 2.19 divided by 10, okay, gives us 0.219. So this is one standard error, right? One standard error is 0.219. How many standard errors is this? Right? So we just divide the 0.5 by 2.19. Okay? We do that, 0.5 divided by 2.19, and we find that this difference is 2.283 standard errors. Okay? So if we go back to our graph, okay, to go from here, 100.5, to here, 100, is 2.283 standard errors. Okay? Everyone with me so far? Everything making somewhat sense? Maybe not yet, but it will. Okay? Okay. So, 2.283 standard errors. We know that one standard error, 68% of the data. Two standard errors, 95.4% of the error. Okay? Three standard errors is like 99%. Okay? Over 99%. So T is the number of standard errors between the sample mean, 100.5, and the hypothesized mean. 68% chance that the real population mean, all the pills in the world, is within one standard error, and 95% chance that the real population mean is within two standard errors. Now, fortunately for us, you've got two choices here, right? You can either get yourself a statistics book, okay? And if you go to the back of the statistics book, it'll have a big table. And the table will have all the calculated values for our T distribution. Okay? Or you can do it an easier way, and you can use Microsoft Excel. Microsoft Excel has a little function which will allow you to calculate a thing called a p-value. Now, we'll come back to what that p-value is just in a second. We'll just focus on calculating it first. So we use this formula, okay? T.dist dot 2t, okay? And then we put in the number of standard errors, okay? The t-value, okay, 2.283. And then we put in the degrees of freedom, which is 99, okay? Now remember we talked about degrees of freedom last week. We said that the degrees of freedom is the number of samples minus 1, okay? Now our number of our number of pills was 100, right? So 100 minus 1 is 99. Okay, so we put in 2.283 here, and then 99, and then you press enter. It will give me this value, 0.025. Okay? Okay. So, in science, we tend to use three different levels of significance. We're in, like, let's say, natural sciences. We tend to use three different levels of significance for statistical testing. Okay? P being less than 0.05. Okay? Statistically significant. Okay? P being less than 0.01. It's very significant. Okay? P being less than 0.001. It's extremely significant. Okay? So this is below 0.05. Okay? So we would accept, because P is less than 0.05, that we accept that the observed difference, my mouth is not working well today, you can tell, right? The observed difference and the hypothesized difference are probably not the same. Okay? The difference between the observed and the hypothesized means is unlikely to be a result of chance. Okay? Let's just flip back to our horrible, terrible chart. Okay. Is our measured value 100? Yes, okay, no, okay. Is our measured value 100? No, right? Our measured value is 100.5. Okay, so it's not 100. So it could be the null hypothesis is false, okay? Could be that the null hypothesis is true. So what we do is we do our one sample t-test. And our one sample t-test says that it's unlikely to be the result of random chance, right? The null hypothesis could be true, and the real value could be 100, and it's just random chance. But our t-test says that this is probably wrong, right? This is probably wrong. And if this is wrong, we accept this as being true, right? We can ignore this half over here, right? But if we say that this is probably not true, it would mean that this probably is true. Our null hypothesis is false, which means that our vitamin Y content is not 100. Okay? And that's the logic there, right? That what we're trying to do is we're testing this one here. We're testing that our result is just random variability in the data. And we're saying that this difference, this 0.5 difference, is probably not random variability. Okay, it's probably not random variability. And if it's not random variability, that's wrong, and this is true. Probably true. Unfortunately, in statistics, we don't get to say things are definitely true, definitely false, right? Science can't give you truth with a capital T. It can only give you probability, okay? So, we calculated our p-value, it gave us this value, 0.05. And we say that the difference, the 0.5 difference, is unlikely to be a result of chance. If it's not a result of chance, then it should be a real difference, okay? So, we can say the pills have a vitamin Y content which is statistically significantly greater than 100. Okay. So we've got this p-value thing here, and we want to talk about that. Let's see if I can get my clicker to work. Okay. So we've got this p-value. Okay. So statistical significance testing is based upon this normal distribution, right? This sigmoidal curve, the Gaussian curve, bell-shaped curve, right? Now, mathematically, it never goes to zero, right? If you draw this graph up, right? So it's got the x-axis coming along here, and it's got a peak here. Let's see, that's not a very normal distribution, is it? Terrible. Okay, so we've got our peak which comes like this, and then it curves down like this, okay? But it never ever goes to zero, right? This will always be above zero. It'll get really close. It'll get down to like 0.0000000000000000001, but it'll never get to zero, right? It never reaches zero, okay? So statistically, no result is ever completely impossible. Well, some are more unlikely than others, right? If it gets to like 1 in 10 billion chance, it's probably impossible, right? But statistically, it never ever goes to zero. Right? That's just the math, okay? And the logic. What a p-value tells you is the probability that the result that you got was a result of random chance. If you make the assumption that the null hypothesis is true. So, if we assume that the mean value actually was 100, what's the chance that we would get this value of 100.5 just as a result of random variability? It's possible you would, right? Because if you imagine that this is 100, okay, and this is 100.5, okay, there is a probability here that it could just be random chance. It's a really small probability, okay? In our case, it's only 2.5% chance, okay? There's only 2.5% chance that we measured 100.5 and it was just a result of random variability. Okay? If the real mean for the whole population was actually 100, but we measured 100.5, the chances of that happening are only 2.5%. Okay? Because our p-value was 0.025. Okay? If we went for 100.4, okay, maybe the chance there is 5%, okay? Okay, which would be a 5% chance, okay, or whatever. If we went for 100.2, maybe the chance there is 0.4, okay? In which case there's a, no, 40% chance. So if we'd actually measure 100.2, maybe there's like a 40% chance that that 0.2 difference was just random variation. Okay? There's a lot to think about here. I know that. You're going to have to go back and watch the video. Okay? You're going to have to turn this over in your mind a little bit. But the p-value basically tells you what's the probability that the result that you got was just random chance. Right? What is the probability that the result that you got was just random chance? If it's below 5%, we accept that there's a real difference, that it's probably not random chance. Okay? So our p-value is 0.025. Yeah.
So, do you reject the null hypothesis?
Below 0.05, yeah. So, literally just what I was going to say next. So we would reject the null hypothesis with a p of 0.025. Okay? If this was 0.05, we would reject the null hypothesis. Okay? If it was 0.06, we would not reject the null hypothesis, we would accept the null hypothesis. Okay? If it was 0.1, we would accept the null hypothesis. It has to be less than 0.05, and then we will reject the null hypothesis. So, given the data distribution that we actually have, if that's representative of all the pills in the world, okay, if we calculated out hundreds and hundreds and hundreds of means, we would expect to get a value of 100 or less in about 2.5% of samples. I'm going to redraw this graph in a different way. Actually, I'm going to rescale this graph. I'll keep my masterful curve here. Okay. So if our mean value here is actually 100.5, that's what we actually measured, right? Okay. And 100 is over here. So what we said is if you go one standard error out, 68% chance, right? Two standard errors out, 95% chance. So we measured 100 pills and we got a value of 100.5. Then we go and we measure another 100 pills. We probably don't get 100.5. Maybe we get 100.4, maybe we get 100.6, maybe we get 100.2, maybe we get 100.8, maybe we get 99.8. We might get a value down here. If we measured another 100 pills, we could get a value down here. Right? If we measure another 100 pills, maybe we get a value of 100. It's possible, right? Because this is the way our distribution works. It's possible to get a value down here, right? But if we assume that our 100 pills is representative, right? We might calculate a mean down here, but we would expect any value of less than 100. If we measured the mean 100 times, then we would expect 2.5% of the means to be 100 or less, just as a result of random chance. So if we measured the mean 100 times, in 2.5% of cases, we would expect to get a mean that's less than 100, or 100 or less. Okay? That's what this is saying, okay? So given our data distribution, if we calculated the mean many more times, we would expect to get a value of 100 or less in 2.5% of cases, just as a result of random chance. Okay. Okay. I know. Terrible. Okay. Terrible. There's a lot of thinking in there, right? So you're going to have to go back and read this again and think about it again. So I want to move on a little bit to a thing called a one-tailed test. Okay? One-tailed tests. So what we used was a two-tailed t-test. Okay? And it looks at both tails of the distribution. But in some cases, we're only concerned with what happens at one tail of the distribution. Okay? So for example, maybe the FDA changes their rules. So what they say is that the pills have to contain at least 100 units. Now, in the previous case, they said that it has to contain 100 units, right? So it could be less than 100 units. If we measured that 100 pills, it could have given us a value less than 100 units. It could also have given us a value more than 100 units, right? But in this case, it has to contain at least 100 units. So we only care about values less than 100. We don't care if the actual measured value is 1,000 or 10,000 or 100,000 or a million, right? We only care about the minimum value, okay? So let's go back to our horrible graph again, okay? So our blue line, okay, this is our proportionate pills, right? This is our standard deviation, okay? This is our pills actually going out here. Our mean is this red line, right? Our measured mean, our sample mean is 100.5, right? And we expect that our mean actually falls inside, our real mean actually falls inside this red curve, okay? Our real mean probably falls inside this red curve, okay? Now for a two-tailed distribution, we actually care about both tails. We care about down here, and we also care about up here, right? So if the rules say that it has to contain 100, we care about both the minimum and the maximum values. But if we're interested in a one-tailed test, we only care about the minimum value. We don't care about the maximum value at all. Okay? So you can do a thing called a one-tailed t-test. Our null hypothesis is a little bit different here. Mean vitamin Y content is less than 100, and our alternate hypothesis is that it is greater or equal to 100. We can assume the null hypothesis to be true, and so we want to find what's the probability for this alternate hypothesis. And we can go out and we can do a slightly different function, t.this.rt, and then put in the same t-value and the same degrees of freedom, and it gives us a p-value which is about half as big as the previous one, 0.011. Now, I don't want to go through the logic and the mechanics of this too much because it's going to take a lot of time. We don't want to spend that time. And I don't think it's very important. But what I actually want to do is I want to give you a caution, right? The p-value for the two-tailed test was 0.025. The p-value for this is 0.01. 0.01 is smaller. Wow, that's great. What if the p-value for the two-tailed test had been 0.06, but the one-tailed test was 0.03? If the p was 0.06, we would accept the null hypothesis. If the p-value was 0.03, we would reject the null hypothesis. So there's a temptation, right, to gain your results. You do your experiment and you get a p-value of 0.06 and you go, oh, it's not statistically significant. Oh no, what shall I do? And then your friend says, hey, why don't you use a one-tailed test? And now your p-value is 0.03 and you go, yay, now it's statistically significant, now I can publish. But you've just gained the results. Now there's two things to say here, right? Number one, don't use one-tailed tests unless you have a directional hypothesis. By a directional hypothesis, what I mean is, I hypothesize that the measured value will be bigger than, or it will be smaller than, right? The two-tailed hypothesis is just it will be different. You don't say bigger or smaller. But for a one-tailed test, you have to say it's going to be bigger or smaller, and you have to do that before you do the experiment. Right? You have to have a good theoretical reason to expect your value to be bigger or smaller or whatever. Right? So don't game your results. It's dishonest. Right? And it will give you false positives. Right? You will present things as being true when you don't have good evidence for it. Now, maybe you think to yourself, yeah, but that's great, I can publish a paper. But here's the thing is that you're publishing something which is wrong. And it's something that which you probably know is wrong. How do you think this benefits science as a whole if you publish stuff that you know is probably wrong? Who thinks that makes the world a better place? No, I didn't think so. Okay. So don't, basically what I'm saying here is, you're almost never going to have to use a one-tailed test. Right? Don't fall into the trap. I see it all the time, people are like, I'll use a one-tailed test, and they're gaming their results. Right? It's dishonest, so don't do that. Sometimes there's a good reason, right? I expect that this will increase the size or decrease the size. You can use a one-tailed test ahead and fine. But if you don't have a good reason to say that you think it's going to be bigger or smaller or airier or faster or whatever, then two-tailed test is better. Okay, so I want to move along to a slightly different example, paired t-test. Okay? Now in this case, we've got two samples, a control sample and a treatment sample. Well, okay. We use a paired t-test when we want to see if two things are different, two samples are different. And we have a good reason to pair the samples. Now I'm going to give you two examples here, okay? But why am I including this now? Well, it's because it's a one sample t-test. Right? The logic behind it is a one sample t-test, so it shouldn't be too hard for you to understand. Okay? So let's imagine that we're ecologists and we're going to do an experiment. And we have this hypothesis that rabbit grazing affects the biomass of alpine meadows, right? So you've got your alpine meadow, you've got your ecosystem, right? And you think that rabbits going in and grazing it is causing damage, right? So you want to measure this, okay? So what you do is you get a bunch of mountains, okay? You get a bunch of alpine meadows, and you set up little enclosures, okay? So here we've got 3 mountains, okay? And we've got one which is a control enclosure, right? We put a fence around and we stop any rabbits from getting in. And then we get another little fence, right? And then we put some rabbits in there, okay? And so you've got control and grazed. And then you've got a second mountain and control and grazing, a third mountain and control and grazed, okay? Now you have to have different mountains, okay? You have to have different field sites, okay? You could put these all on one mountain, but then you'd suffer from a thing called pseudo-replication. Right, false replication. So you need to have different field sites. You need to test this in different places to see if the conclusions hold up. So you've got 3 mountains. Mountain A is sunny and warm. Mountain B is sunny, but it's kind of cold. And Mountain C is cloudy and rainy. Okay? Now, we would expect that because of the climate conditions that we would see differences, right? Probably we would expect that the grass grows faster here and slower over here, right? It probably grows slower in the cold, wet environment, and it probably grows faster in the nice and warm environment. So we would expect differences between this mountain and this mountain just because of the climate, right? Irrespective of the treatment. So what we need to do is that we're going to pair the plots. And we're going to say that this is pair 1, this is pair 2, and this is pair 3. And if we put that into the analysis, then we should be able to find the differences between these and these and these, right? Because what we're going to do is we're going to compare this one to this one, we're going to compare this one to this one, and we're going to compare this one to this one, right? We're just going to look for the difference. What's the difference between these two? What's the difference between these two? And what's the difference between these two? Okay? So we pair the plots, and this allows us to account for outside variability. Okay? So our variability here is about climate. By pairing the plots, we can get rid of that factor, right? Because these two have got the same climate. The difference between them is real. It's because of the treatment. Okay? So we'd expect plants growing in sunny, warm environments to grow faster than those in cloudy, rainy environments. And our paired t-test lets us take the background differences away. It lets us control for variability. It lets us control for background variability. Okay? This is a homework question. Okay? Paired t-test lets us take away background variability. Okay? So we'll see an example. Okay, so we're going to have a different experiment. So let's imagine that we're animal scientists, okay? And we're going to do an experiment looking at the growth rate of mice. Okay, or it's an experiment on something, but we need to test this, okay? So we want to look at the growth rate of mice. And we measure the weight of the mice on day 14 and day 7. And we want to see, are the mice bigger on day 14 and 7, right? So the mice when they're 7 days old, tiny, right? Okay, when they're 14 days old, they're going to be a bit less tiny, right? We expect they've grown over that time. Now, we're going to re-weigh the same mice. So we want to use a paired t-test. So here's our data, okay? Here's our animal number, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's our weight at day 7, okay, in grams, 1.0, 1.3, 0.9, 0.8, 1.1. Here's our weight at day 14, 2.5, 2.6, 2.5, 2.2. Okay. And this is the difference between day 7 and day 14, right? So 2.5 minus 1, 1.5. 2.6 minus 1.3, 1.3, okay? 2.5 minus 0.9, 1.6. This is the difference, okay? Now, think about it this way, right? Look at this mouse down here. It's 2 grams on day 7, right? But this one, that one actually, that's the smallest one, is 0.6. That's quite a lot of variability, right? We would expect at day 14, we'd expect this mouse to be bigger than this mouse on day 14, right? And it is, right? So this goes from 2 to 3.6, and this goes from 0.6 to 2.1, right? Now the differences are actually fairly similar. The differences are 1.6 and 1.5, right? So we've got rid of the starting weight variability, we've got rid of it, right? By taking away the first data point from the second one. By pairing the samples, we get rid of background variation, okay? So we're left with these differences, okay? And we can take a mean of these differences, and it gives us 1.26. And we can take the standard deviation for these differences, and it gives us 0.536, okay? Now, we have a null hypothesis, right? Our null hypothesis would be there's no difference between day 7 and day 14. That would be our null hypothesis, right? That there's no difference in mass between here and here, right? Because our null hypothesis is always no difference, okay? So our null hypothesis, there's no change in mass over the 7 days. Our alternate hypothesis, mouse mass is different between the 2 days, okay? This is actually badly framed here, okay? It should actually be that there's no difference, okay? But we'll use less structured language, okay? So null hypothesis is that the average mass on day 7 and the average mass on day 14 is the same. The alternate hypothesis is that there is no difference, right? There is a real difference between the 2 days. So we can use basically our one sample t-test measurement here, right? our mean of x, or mean of the difference, right, is 1.26, was it? Yeah, 1.26, okay, x bar d. 1.26, and our standard error goes on the bottom, okay? Now our standard error is our standard deviation, which was 0.536, divided by the square root of the number of samples. Now our number of samples was 10 in this case, right, 10 mice. Square root of 10 is like 2.5, 3.1, something like that, okay? So, we put 1.26 up here, we put 3.1 or whatever it is down there. And we get a t-value, oh sorry, that gives us the standard error, we put the standard error down here. So our standard error is going to be 0.536 divided by the square root of 10, which is 0.169, okay? Our t-value is going to be 1.26 divided by 0.169, okay? And this is going to give us a t-value of 7.46 with 9 degrees of freedom. Now, we're going to stick that into our Excel function, and it gives us a p-value of 0.0000193, which is pretty small, okay? Our p-value is so small that the difference in mass between day 7 and day 14, it's unlikely to be a result of chance. It's almost definitely not a result of chance, right? There's only a 1%, 0.1%, 0.01%, 0.001% chance that it's just random, right? It's far less than 1% chance that it's random, okay? That would be a 10% chance it's random, 1%, 0.1, 0.01%, 0.00019% chance. A really small chance, yeah? Okay. So, actually write that 0.0000193. We'll get rid of the first two places there. So 0.00193% chance that the difference that we find is just random variation, right? Which is tiny. We're 99.99% sure that this difference is real, that it's not a result of random chance. Okay? We're 99.99% sure that this is not a result of random chance. So our p-value is much, much less than 0.05. We reject the null hypothesis. Our null hypothesis was no change in mass, and we accept the alternate hypothesis that there is a change in mass. Okay? And I think if you look at the data, it should be fairly obvious that this goes from 0.9 to 2.5. Okay? But we used a pairs t-test because it let us take away the background variation between this mouse and this mouse. That background variation went away. Okay? Now, we have got through an awful lot, so we've got 2 minutes left, so we're good. We've got through an awful lot of stuff today. There's a lot of thinking there, right? And a lot of it is really non-intuitive, right? Because in statistics, you have to use a lot of double negatives. And that's really hard, right? But it comes down to this core. Let's assume that your null hypothesis is true. Your treatment does nothing. Okay? You've got a difference between the hypothesized mean and your measured mean. Right? That difference could be just a random result of chance. If your treatment does nothing, then you can still get values which are not on the population mean. Your sample mean can still be different from your population mean. Okay? Let's imagine I am the population mean. Okay? Here is the sample mean. Okay? There's a difference between the population mean and the sample mean. What is the chance that that's just random chance? What's the probability that the difference between the sample mean and the population mean is random chance? That's what the p-value is telling you. Okay, that's what a t-test is telling you. Is the result that you measure, is it random variability or is it not random variability? What's the chance that the result that you got is just random statistical data noise? That's what we're trying to go for. So much thinking today, I know, okay? Go away, I'm going to stick this video up this afternoon, watch it again, read through your notes again, think about it some more, try, do what you need to do. Homework, we'll see you tomorrow, okay? Good luck. It's not so hard, right? I think. Oh. Good luck. Our null hypothesis was that it's less than 100 years. We reject that because our negative value is 1.5. What does it feel that you get a value of 100 or 100 or less? You don't expect to get anything like I have great confidence in you. Hopefully it's recorded sometime.